Today I will present an exercise from the book Gourdon Analyse by Gourdon about the algebra of continuous functions on a compact set. So let X be a compact metric space, D the distance function, and CXR the set of continuous functions from X to R endowed with pointwise addition and pointwise multiplication of functions. So for all point S in capital X, let us denote I subscript S, the ideal of functions that vanish at this point. In the first question, we will show that any proper ideal is contained in an ideal of the previous form. And secondly, that the maximal ideals are precisely of this form. There's a bijection between points and maximal ideals. Maximal in what sense? So the set of ideals is partially ordered by inclusion, and an element I is maximal if whenever an ideal J is comparable or bigger than I, then either J is equal to I or it is equal to the whole algebra. And lastly, we will see that algebra morphisms from this algebra of functions to R are of a very specific form, namely that to a function they just associate its value at a certain point. So again, there will be a bijection between algebra morphisms and point. And this correspondence between algebra morphisms, so here with value in R, they are known as characters. They are elements of the dual of the algebra. So correspondence between algebra morphisms, ideals, and points is at the heart of commutative algebra and algebraic geometry. So maybe not necessarily with a maximal property. So let me just mention, for example, the definition of spectrum of a ring. It is just a set of prime ideals. So those are the main ingredients of the commutative Gelfand representation theorem. So in the context of commutative C-star algebra, it says that there exists a topological space such that the C-star algebra is in fact the algebra of continuous function on that topological space. Here we have restricted to metric space just to follow the book, and I will point out at which point I use the distance. Let me just finally mention that there's a version for Banach algebra where the functions are, it generalizes to algebra of functions that are more general than just continuous functions, and also a non-commutative version known as Gelfand, Naimark, and Segal, which is also crucial in the algebraic approach to quantum mechanics. So first question, let I be a proper ideal. We need to show that it is included in the ideal of the form IS. It means there exists a point such that every function in the ideal vanish at this point. If by observed it is not the case, if for any S you can find a function in the ideal that does not vanish at this point, then by continuity of this function fs, there exists a neighborhood of the point S, so here a ball of radius delta, such that the value at x and value at s are close. So yeah, if I take epsilon precisely smaller than the absolute value of fs, for example half, there exists this neighborhood such that fs at x does not vanish. For example, if the value here is negative, I obtain here minus 3/2 the absolute value and minus 1/2 the absolute value. We see that this does not contain 0. And if I take the square of the function, we'll have a function that is strictly positive in that neighborhood. Of course, delta here implicitly depends on epsilon and s. We do this for all s, so we obtain a cover of the compact space, so we can extract a finite subcover of open cover, and because it is finite, we can consider this finite sum. So for a given I, this fsi square, it is strictly positive in one of those balls. And then we add other terms that are non-negative, so positive or zero. So the result is strictly positive everywhere, and it consists of element in the ideal. So because these capital F never vanish, we can consider the inverse. It is indeed a continuous function. Capital F is in the ideal, and if we multiply by something else, it stays in the ideal. So we see that the function that is constant at 1, so the unit of the ideal, is inside of the algebra, is inside the ideal. And if I multiply by any element of the algebra, it will be in the ideal. So we have equality of the ideal with the algebra. So this contradicts the fact that we chose a proper ideal. So any proper ideal is contained in an ideal of the form I subscript S. And those ideals are precisely maximal ideals. So let us first show that this is a maximal ideal, and then that the maximal ideal is of this form. Indeed, if I take two functions that vanish at S, their sum and product will vanish at S. And if I take a function in this ideal, I multiply by an arbitrary function or by a constant, it will again vanish at S. So this is an ideal. To show that it is maximal, we take ideal that is bigger, contains IS. We need to show that either it is equal to the whole algebra, or if it is really a proper ideal, then it is equal to IS. If it is really a proper ideal, by A, it must be contained in an ideal of the form I subscript T. Let us now show that T has to be equal to S. If it is not the case, then we can consider this continuous function that to X associate the distance to S. We see that it vanishes at S, but if T is different to S, then it will not vanish at S. So it will contradict this. We'll have found a function that is here but not in here. It will contradict this inclusion. And here is where we use the distance. So in the topological framework, it is just difficult to show existence of a continuous function that separates 2 points. So here by absurd, T has to be equal to S. So in that case, J is in between IS and IS. So it has to be equal. Conversely, if I have an arbitrary proper maximal ideal, if it's a proper ideal, then by A, it is included in an ideal of the form I subscript S. And because it is maximal, we have either equality or IS equal to the whole algebra. But there are functions that are do not vanish at S. So this case is excluded, so we only have equality. Maximal ideals are of the form I subscript S. And let us now look at algebra morphisms. And we said that they are of the specific form that to a function f, it associates simply the value at S. Let me just recall the definition of algebra morphism. So it is, you probably already know. So it preserves the sum, it preserves the operations. So addition, if I multiply by a constant lambda, so this is linearity, and it also preserves the product. So if f and g are in the algebra of function, it gives phi of f times phi of g. I just wanted to add that in the context of unital algebra, it maps the function that is 1 everywhere, the constant function at 1, which is the unit of the algebra. So algebra, a function I denoted A, it maps it to the unit. So as linear map, an algebra morphism is a linear map plus something. You can notice that it is kind of normalized. So you notice that if you consider 2 times phi, it will not be an algebra morphism. And of course, because the target space is of dimension 1, if it's not the trivial map, so in fact here I exclude the trivial map, phi will be surjective. So let me just write. Of course, you can obtain y as this number times the unit, so it gives y. And the last point is that the kernel of an algebra morphism is an ideal. So for all f in this ideal, for all j in the algebra, of course phi of fj, it is commutative, so phi of jf, it is phi of f, this gives 0 times phi of j, so f times j is equal, phi of this element is equal to 0. So the kernel is stable, of course, under sum, and stable under multiplication by an element in the algebra. So it is a kernel, and phi will be surjective if it is non-zero. So this is what I write. Kernel is a proper ideal, and because phi is surjective, we will show that the kernel is a maximal ideal. So the definition we need to check is that either J is equal, and if it is not equal, we must show that J is the whole algebra. If J strictly contains the kernel, there will exist an element that is not in the kernel. If A is not in the kernel, phi of A is not 0. So this is a real number that is different from 0. So it admits an inverse. And because phi is surjective, this inverse, we can write it in the form phi of something. 1 itself is phi of the unit. So I use that phi is an algebra morphism. I put everything to the left. Phi is an algebra morphism. So I can write phi of this thing equals 0. So it means that this is in the kernel. So now k in the kernel, it is also in the algebra. So I obtain that A is in the algebra, in the ideal. I multiply by something, it stays in the ideal. K itself is in the ideal. So the unit itself is in the ideal. And again, if the unit is in the ideal, I multiply the unit by anything of the algebra, it stays in the ideal. So A is contained in I, so J must be equal to the whole algebra. So if the kernel is a maximal ideal, we have seen that it is of the form I subscript s, and let us now show that in fact it is of codimension 1. It means that A, the whole space, is kernel direct sum with a line. So otherwise the kernel is a hyperplane. Let me just give intuition for this, and also a justification of property that we will use right afterward. So phi, our algebra morphism, let me schematically understand A as the 3-dimension space, and kernel as a hyperplane. So let me give an intuition for this. So kernel is level set of 0, and let us imagine that the function is non-zero. The algebra morphism is non-zero. So if, for example, I have 0, and for example, this is equal to 1, and what we notice is that if I add an element in the kernel, this will also give 1. So it says that the level set of another point, so here of 1, in fact is a copy, a translation of the kernel. It is all the elements of the form a specific solution plus plus a homogeneous solution, like this. So in fact, I have for every time I can parameterize. Let me write like this. I will parameterize the set of level sets, so phi minus 1 of y, by the values in the target space. Every time I choose y, here I have phi minus 1 of y, and they are of a specific form, one specific solution plus the kernel. So all the level sets are copies, are translated. So we can understand this in two different forms. So if I take, for example, here I have a vector, I can either understand that we have the decomposition of the initial space as kernel and the one-dimensional space generated by this, and in fact every time I choose one element in that direction, Ka, it gives me one level set. So here there's one intersection. So I can parameterize the set of level sets. So this is the definition of the quotient. The quotient is the set of level sets. I can either say that I can take one element in here, it gives a level set. So I take one element in here and I obtain a level set, or I can write that directly it is the disjoint union of all the level set. So let me write, for example, a coefficient. So I can write also parameterize with y, or I can parameterize with an arbitrary number. And it's something, a multiple of a0 plus kernel of phi, like this. And this is true for any, if I choose any supplementary space to the kernel, then I have a bijection between element in this direction and level set. So if I have A here, an equivalence class will be A plus kernel. And now the isomorphism theorem basically says that to this element plus kernel phi, you simply associate the value phi A. And this map between the set of level sets and R is now a bijection. So now the question is, what happens if I have another linear map that has the same kernel? So kernel of psi equals kernel of phi, and in fact it will give rise to the same partition of A. So algebraically we just write that this gives a certain value. If it is not 0 everywhere, so it has the same kernel, so it is not the 0 map, then we can see that mu alpha, here it is equal to lambda phi of 1, phi of a0, and we have said phi of a0 is 1. So this will give lambda, mu lambda 1. So it is lambda of phi of mu a0. I just want to say that psi is, as a function, it is equal to lambda phi. So this is just gives that the geometric interpretation is that if I have another linear map that has the same kernel, then it is proportional to phi, because these kind of functions, they are completely determined by their value at one point in a direction that is not in the kernel. Just take here, you can take one point in here and you just look at the value of the function here and it will completely determine the function. Okay, so and this is what I use right afterward. So we have said that kernel is equal to I subscript s, and we notice that the evaluation map, so the function, the algebra morphism that to a function associates its value at s, has kernel is. Kernel is the ideal of function that vanish at this point. And what we are saying is that this linear map, linear form, is in fact proportional to our original algebra morphism. And here, if our algebra has a unit, so here it's a function that is constant at 1, I just evaluate here at the unit and here also at the unit. A function that is constant at 1 evaluated at s, it gives 1, and phi of 1 is 1. So I obtain directly that the coefficient of proportionality is 1. The book uses a different argument, which will hold in the case of non-unital algebra. So let me just give this example. If I have a space such that every point has a compact neighborhood, so it's called locally compact, I can consider the function that vanish at infinity. So what it means, a function vanish at infinity if for all epsilon strictly positive there exists a compact set such that outside of this compact set the function is smaller than epsilon. So this is an algebra, and it does not have a unit because the function constant at 1 does not vanish at infinity. And we can still prove that the proportionality coefficient is lambda. So there will exist a point, let's just pick a point where the function is non-zero, just pick a function and a point where it's non-zero, and thus look at the evaluation of f square, because the evaluation map is proportional to lambda. It is phi of lambda square. Because phi is an algebra morphism, it's phi of f everything square. And here we write again that phi is proportional to evaluation. It's evaluation divided by lambda square. And now I use the fact that f square at s is different from 0. So I simplify here and here, obtain that 1 over lambda is equal to 1, and thus the lambda is equal to 1. So if we want to summarize now, so in the first question, which is just basically a technical question, we see that every ideal is included in the maximal ideal, and the maximal ideal in the second question, they are precisely of the form the function that vanish at one point. So there's a bijection between point and maximal ideal. And finally, that every algebra morphism, so its kernel, it is in fact maximal ideal, and so the algebra morphism will be proportional to the evaluation map, and the proportionality coefficient is 1. So every algebra morphism is in fact evaluation at a certain point. So thank you for your attention, and